Thanks, Nick. Thanks to the organizers of the workshop and the program. I'm really excited to be giving this talk. So, the first thing I want to say is that I don't know about you, but I feel like you shouldn't really apologize for things you can't control. But with that said, I apologize for being a theoretical computer scientist. So I'll try not to bust out complexity classes and stay away from asymptopia. But okay. So the second thing I want to say is I think I finally caught on to what's going on here. So, if you've been at this workshop or the previous ones, I think there's like a secret contest to see who can get through as few of their slides as possible. So, I think my main competition right now is Nathan Weeb, who only made it. He took 30 minutes on his first slide. So it's kind of hard to beat that. But please, I need your help. So, okay. So I want to tell you, what I think of as quantum optimization. So for me, it's this box. And we have classical algorithms on the top, and we have quantum algorithms on the bottom. And stuff you may think of as like physical stuff or like classical optimization, to me, they all look the same. And so I want to convince you, hopefully, that this isn't like some crazy thing, some crazy way of thinking about all of this. So I don't know. Let's see. Oh, okay. Here's a pointer. Yeah. So really, everything we do is kind of at the top row because we only really have classical computation to do kind of cutting edge things. So, and of course, we want to be doing more things on the bottom row. But, whether you think about things physically or you think about things classically, I want to think about them as an optimizer. So, in particular, I think that quantum optimization problems, including finding extremal energy states and other properties of local Hamiltonians, aren't really that different from classical optimization problems. So this is my thesis. And then second, we really need to exploit this, and there aren't enough people doing it. And part of the reason is enough people aren't really, talking to each other or kind of speaking the same language. So that's where we're starting with this. And then, let me kind of motivate. So what I really want to do with this is I want to give you several examples of how kind of merging these classical and quantum viewpoints can actually get you something new and interesting. So, we all know Alice. And Alice has a problem she wants to solve. And there's Bob. And Bob, you may call him an optimizer, but I needed something that started with a B. So Bob takes this problem, and Bob solves it. And everyone's happy, except that's really not how things work. Because what usually happens is that Bob solves it, and then Alice is like, oh, yeah, good job. But that wasn't really the thing I was looking for. Because there's some secret sauce, right? Like there's always secret sauce. So the universe gives us lots of secret sauce, and we take it and we turn it into these nice toy models that we try and solve. But really, once you solve them, there's so much more nuance. And somehow, each time you solve something, you want to get like a progressively better approximation of the thing you really cared about. So Alice says, okay, I'll give you some more secret sauce in my model. And then Bob, gives another solution. And then this kind of keeps going on and on. And so how do you break this cycle? How do you break this loop, right? So we saw the transverse Ising model in Abhinav's talk just now. And the first thing I want to say is that, well, there's already something kind of classical about this. I mean, it's kind of funny, right? Like a lot of my physicist friends will say, oh, this is just a classical problem because it's stochastic. And, yeah, sure, you have a ground state, but all your amplitudes are without loss of generality non-negative, and so you could just think of them as like a distribution. But there's still something quantum going on, and this can capture NP-hard problems. This is actually stochastic MA complete, if you know what that is. I know I broke my promise, but sorry. So how is this going to help us? Okay, so first let's look at the first term. And if I just think of the distribution here, and I kind of ignore that this is coming from a state, what I really get is that the first term is just taking some expectation over a classical function that assigns -1 and +1 values to these classical variables, okay? And then if I look at the second part, well, what am I doing? So this one is a little more interesting. So if I think of this as a distribution, now what I'm getting credit for is I'm getting credit for support in the distribution on strings that differ in exactly 1 bit. That's what the transverse field here is doing, right? So you're looking at x on each site, and so you're really saying, hey, if I sum up over all of these, I only get credit when I have 2 strings that differ in bit, in the first bit, the second bit, third bit, so on and so forth. So if I put all of this together, then my transverse field Ising model, thinking about it completely classically, just becomes this problem where I'm trying to tailor a distribution, so I'm optimizing over distributions here, where I get some classical expectation value, and then I get credit for diversity. And so how does this help Alice and Bob? Well, what Bob can do now is he can say, hey, I'm just going to build a distribution, and yeah, the original thing Alice wanted to do, I'm going to kind of put into this classical objective, but in addition, I'm going to kind of try and get a distribution over diverse strings. And that way, if I just give Alice access to this distribution, she can sample from it, and if she doesn't like the first thing she gets, she can take the second thing, and she can do all the work of this iterative process. And so this idea of being able to access diverse but still high-quality solutions is something that classical folks think about all the time. And so, people don't usually think of transverse field Ising that way, but it's a valid perspective. And so, maybe making things accessible to classical folks in this kind of way might help some cross collaboration. So yeah, now the story's kind of nice. We have the problem, and then we have Bob, and Bob gives some access to sampling this, and then Bob's done, right? So what I want to tell you about next, so that was taking a quantum problem and trying to put a classical spin on it. Now I'm going to end up with a quantum problem, but I'm going to start with something that's completely classical. Okay, so oops, I pressed the stop button, and it works. Okay, there we go. All right, so you have a graph, and then many of you in the audience are probably aware of what a Laplacian of a graph looks like, and then we know how to take maximum eigenvalues. And so this problem where someone gives you a graph and you output some eigenvalue of it, or the max eigenvalue of it, is a well-solved problem. It's in P. I mean, this thing is so well solved. When the kids are like on their phones and doing this thing, they're solving these problems. It's so well solved that I bet like many of you in the audience are like solving these right now. I would ask for a show of hands, but I'm afraid there'd be so much enthusiasm that someone might pull a muscle, so I'm not going to, right? But this is a super well-solved problem. So how do we put a spin on it to make it more quantum? Well, the first thing, let me ask you, is what happens if I give you a super simple graph, right? Like if I tell you, okay, I want to do this thing for a cycle or a complete graph. Does that make the problem easier or harder? Easier, yeah. So these are like fixed graphs. You give me some number of vertices. These are fixed graphs, and I can just kind of write down the solution right on a piece of paper usually for this kind of thing. And okay, so you're like, okay, that's a very easy thing to do. But the twist kind of is that again, as a theoretical computer scientist, something kind of gets a little worrisome about that, because if all of a sudden you're saying for each n, there's only one graph that I care about, then the input size went down. So now the input size isn't the number of vertices or edges in the graph, it's really just this number n. So you give me a number n, it takes log n bits to write down, but I have to solve a problem on a graph with n vertices. So I only get, when I'm talking about the running time of my algorithm, if it's like an efficient algorithm, it better be with respect to log n. So somehow, if you squeeze your input, then you're making things really hard because you're not giving me as much time or space to work with. Okay, so how about if we tried to make this more interesting? What if we said, hey, we have a small graph, and somehow it implicitly represents an exponentially larger graph. And then we have to take the maximum eigenvalue of that big graph. And so now, I'm in a little bit of trouble, because if this operator, if this graph is exponentially large, then finding the maximum eigenvalue might be kind of a hard thing to do. So I don't know, how is this? Does this story kind of make sense about the succinct representation? Getting some nods and other things, but okay, I'll go with the nods. So, okay, in particular, we could now say what we want to do is I give you the graph and I give you some numbers, and these numbers are inverse poly close in the size of the original graph. Yeah, I mean, there's a mistake here. This should actually be, the size of the input, which isn't the size of the graph. Like, oh, sorry, no. I'm confusing myself, right? The Succinct stuff is confusing. Yeah, the input is a small graph. So this is actually inverse poly in the size of the small graph. But then you build a larger graph, and now, I'm telling you the maximum eigenvalue is larger than B or it's smaller than A. That's like the promise I'm giving you, and then you have to decide. So I'm turning this into a decision problem. Yeah?
Why is your input a graph? I mean, you could just say you have a bit string and a rule to produce G prime out of that bit string.
Yeah, that's true. That's true.
Of having a graph.
Yeah, so there's, you're absolutely right that I could just, whatever representation makes sense is the one I should use. But for what I'm about to tell you, it'll make sense for the input to be a graph. So now, we can try and find such a state. And then the nice thing is if we did have such a state, we could use a quantum computer, phase estimation, for example, to efficiently verify this in polynomial time. So in this case, this would actually be the interaction graph of, possibly something like an interaction graph of a Hamiltonian. And so this problem, because you can efficiently verify it, it's actually in QMA. So this is, we don't know how to solve it, but at least we can verify it. And so this is in the same place where we have most of our other interesting local Hamiltonian problems.
Sorry, which condition is it in QMA? Tell us what G prime, like how you get G prime.
Yeah, I'm about to give you an example of how to get a G prime. So I know it's a little nebulous right now, but right now G prime is exponentially larger. And then the condition is just that if someone were to give you a purported state, you could actually verify which of these cases you were in efficiently using a.
I know about QMA.
Okay, yeah.
Interesting QMA to me. My question is, how do I get the graph into the QMA verifier if I have no idea how this is a constructed function?
Yeah. Okay. So let me. This will be the answer. Okay. Yeah. So concretely, I give you a graph. And there is a construction you can do. So this is called, what I would call the generalized Johnson graph. The details, so for the story, the details aren't important. The main message here is that, there is a concrete way to take the small graph and turn it into an exponentially bigger graph. But if you care, the way you do it is that for each, so you pick a parameter k. So in this case, I've picked k equals to 2. But in this graph, all the vertices are going to be subsets of these vertices of size k. So if you make k large, like if you make k like n over 2 or something, now your vertices in your new graph are going to be all subsets of size n over 2 of your original graph. And so that's how you get this exponentially larger graph. Yeah?
So what I would have done is to take a graph and then take the permutation group of the graph. And then I can use the same generators, the same edges here than edges in the permutation group. Isn't that a very natural example? It's just a little bit more than exponential and factorial, but wouldn't that also qualify?
Yeah, absolutely. But that won't give you quantum max cut. So that's, so it turns out.
But it contains all of these guys for every k.
But then is the edge structure the same? So here the edge structure is so what I'm saying is those will be the vertices?
Yeah, it contains all of these guys in particular as subsystems.
Oh, yeah, absolutely, yeah. So I think we're talking about the same thing because these will be irreducible representations of the permutation group. Yeah,
but it's super hard.
Yeah.
If you want to do it by hand.
I don't like doing things by hand, but I'm with you. If you were into that kind of thing, I agree. Okay.
So what is the edge rule?
Yeah, what was that? Was there another?
The edge rule?
The edge rule, right. So the edge rule is that, I take two of these vertices in this Johnson graph, and there are now, remember, they're subsets of vertices here, and then there's an edge between them. If when you take the symmetric difference, you get exactly two elements, and those two elements were an edge of the original graph. So the edges in this graph arise from the edges in this graph, and here I've kind of labeled, where they're coming from. So, this orange edge, for example, when you take the symmetric difference of these two vertices, then you get 2 and 4 left over, and 2 and 4 was an edge of the original graph, so that was this one. There's another one that gives you 2 and 4 here, so on and so forth. So yeah, maybe I should have. Good, thank you for future. For future me will know to present this in a different way to make this less confusing. Okay, So, so what ends up happening? So it's exactly what Maria said, is that, if you actually look at kind of the direct sum of these, so now the problem, again, was to find the max eigenvalue of the Laplacian of this bigger graph. And we could pick k, being the size of the subsets. And if you look at a direct sum of these for all k, it turns out that this Hamiltonian is equivalent to quantum max cut. You don't know what quantum max cut is maybe, but I'll tell you the anti-ferromagnetic Heisenberg model, for example. So this is a completely non-physical way. You could argue how non-physical it is, but at least you didn't need to know any Pauli operators or physics or anything. And moreover, even one of these, I could fix a k like n/2, and that would be an interesting problem on its own. So here was a way of just saying, hey, look, I'm giving you a prescription for taking a small graph, turning it into a big graph. You want to find the max eigenvalue of the Laplacian. That is somehow a quantum problem, whether you like it or not, right? And so this is the idea, can we come up with more connections like this? So I'll tell you more about quantum max cut. In fact, well, not right away, but soon enough. So classical max cut, what you want to do is you want to partition the graph, a graph, into two pieces, and you want as many edges to cross these pieces as possible. So if we call one side of this blue, one side orange, then all these red edges are the ones that cross. And this cuts 7 edges. You could do a little bit better. This is the Peterson graph, if you've seen this before. And you can actually get a cut, I think, with 12 edges. Okay, so it's hard, it's an NP-hard problem. It's hard to figure out what the right answer is. And it's also hard to stare at an answer and convince yourself that it's optimal. So if we want to try and make this something that's going to be more compatible with like a spin system or something like that, then what we're really doing here is we're maximizing a bunch of terms. And for each edge, what we want is we're thinking about assigning colors to vertices. So we're coloring the graph, and an edge is happy if it gets different colors on its endpoints, right? So those are the happy edges. And so if we think of, instead of colors, if we put plus and minus ones, then very much like the classical Ising model, you want different spins on endpoints of an edge. So those are the ones that you're going to count as being cut. And so this is if f is our assignment of plus minus 1 values to the vertices, this function here tells us how many edges we've cut. Okay, and this is exactly 1 if these are different. So like I said, it's NP-hard, and so what we could do instead is we could look for approximation algorithms. So this is a very, when people came up with NP-hard problems, they got frustrated. When they got frustrated, they said, okay, one thing we can do is we can try to approximate things. And then if you're a theoretical computer scientist or a mathematician, you don't want to just approximate things, you want to try and prove things. And so this is where approximation algorithms come from. And so the idea with an approximation algorithm is that I give you some input. We talked about different kinds of input models just now. And then the algorithm is going to output like the solution, or in the quantum case, a state, a way to prepare the state, the description of some circuit. And then what you're saying your value is it's the approximate value over the optimal value. So usually we're going to be talking, usually you may be used to ground energies when you're thinking about local Hamiltonians. Here, just to make things more consistent with the classical problems, let's think about maximizing energy. And so our approximation is how much of the max energy did we earn on an instance. And for approximation algorithms, you're looking at the worst case. So over all instances, what's the gap, this ratio. And there's a difference here in like culture and approach and techniques between heuristics and approximation algorithms. So if you had, like some very nice kind of structured set of instances to solve, you would probably use heuristics, or if you had like a single big instance you were trying to solve, you would use heuristics. These are usually guided by intuitive ideas, and in practice, heuristics work well, or at least we convince ourselves they do, and we don't try too hard to check that, and we move on. But they perform very poorly in kind of the worst case, because worst cases can be like super adversarial, maybe. So, but it's also difficult to prove anything about the performance. On the other hand, with approximation algorithms, it's all about the worst case. So, these aren't necessarily giving you practical algorithms, but you are knowing that in the worst case, you're not going to be surprised. You're proving something about the worst case. And usually these are kind of mathematical because the output isn't to do well empirically, on some test set. The output is to prove that you can get some kind of approximation guarantee. Yeah, yes.
Or just I have a question. And another class of algorithms which is kind of making its rise recently is also the randomized classes.
Yeah.
You're not necessarily interested in the worst case, but you also want to know, okay, if I'm willing to pay more in resources, I have a probability of getting that particular results and so on. So is that kind of also in?
Yeah. So that's a really good point, right? So the worst case is kind of what we analyze because we're ignorant. We don't really want to analyze the worst case. We want to analyze some average case or some practical behavior, but it's really hard to prove things about that. And so this is, the idea here is it's maybe in a few years, ideally this would be replaced by something else. You really want to close the gap between these two. That's the main point. But this is introducing mathematical ideas that could be practical, and this is introducing practical ideas for which you might be able to say something rigorous. But I think the only point I want to make is that they're kind of complementary. They each have something to contribute, and people who kind of maybe should be aware of both or kind of maybe shoehorned into different categories. And so that's why I mentioned it. So, okay, we're going to look at approximation algorithms. Let's talk about max cut. So for max cut, there's a really simple way to get a half approximation. So I can always guarantee I can cut at least half of whatever the optimal solution cuts without knowing what it is. And so what's this algorithm that gets you a half?
It says on the slide.
It says it on the slide. That's right. Yeah, man. Can't get anything past you. Yeah, so, right, you randomly pick the vertices. You take a vertex, independently put it on the -1 side or the +1 side, and if you look at each edge, there are kind of 4 possible assignments to its endpoints, and 2 of those will give it different values on the endpoints, so, we expect that half the edges will be cut. And you can de-randomize that algorithm. You can make it efficient. And so that's our kind of baseline. That's our starting point. And people thought about this for a while, and they got, okay, yeah, we can do a little bit better than a half here. We can get this, improvement in terms of the number of edges. Oh yeah, now we're really cooking. We got improvement in terms of the number of vertices, and okay, improvement in terms of the max degree, but somehow a half isn't really moving. How many years has it been at this point? Okay, so probably a long time, because this was known. Probably in like the 60s or 70s or even earlier if anyone thought about this. And then all of a sudden in 95, you get this 0.878. So you go from a half to 0.878. And what do these numbers even have to do with each other? Why 0.878? So 0.878 is this beautiful algorithm by Gomans and Williamson that's actually based on some previous work of others, who kind of found ways to take maximum cut, max cut problem and relax it to a semi-definite programming problem. You're trying to assign vectors to vertices instead of plus or minus 1 spins. And so this algorithm you can analyze and you can show, hey, look, it's a very natural algorithm, but the performance guarantee is 0.878. So that's not natural. And so is again, is this actually due to our ignorance? Well, no, actually not. It turns out that 0.878 is the best you can do, up to the unique games conjecture, unless p equals np. So in other words, another way of saying this is, we could, in polynomial time, we can approximate all the way up to 0.878, but if you want anything even slightly better, the problem becomes hard. So there's this phenomena, that's kind of, for classical optimization problems, you run into these limits where there are thresholds beyond which it just becomes hard to even approximate the problem. So, this picture is kind of closed if you believe the unique games conjecture. And so then one question I have for you all, and the community in general, is for people who are trying to use quantum algorithms to get advantages for classical problems, why should quantum have anything to do with this picture? Why should this, in order to complete this story, why should we need to know about quantum mechanics, or why should that help us complete a story like this, right? So people, for the quantum approximate optimization algorithm, QAWA as I call it, people like to use max cut as kind of an example, right? And people will have these studies and they'll say, okay, this is the approximation guarantee we get, but what's the end game here? Are you really expecting to beat a classical algorithm? And classically, you kind of get this. I saw a hand go up. I'll get to you in a sec. But, are you expecting to beat this? I mean, shouldn't just we be able to come up with pictures like this for like different versions of classical problems and max cut on different graphs, etc.? Yeah.
I want to give you an answer which you will not like, but or maybe you do, because the proof of that thingy there is related to Grothendieck's inequality, and that the biggest innovation was to go from commutative things to matrices, and the proof is a matrix proof. So whenever you have a matrix proof, you should expect quantum to help.
But there's so I agree that sometimes you could prove things about commutative objects by going to non-commutative objects, and so maybe your story is when you can do that, or when you get an insightful proof in the for the commutative thing using non-commutative stuff, there's somehow underlying quantum stuff going on, and maybe that's the case, but still, I didn't. Okay, we could talk more about that, but in this case, I feel like that would be a reinterpretation of the proof. I mean, there's a perfectly good classical proof that doesn't need anything non-commutative to complete the story. Okay. So that's the first question, is why should quantum stuff, whenever we're expecting some kind of approximation advantage, why should quantum stuff help on classical problems? Where will quantum finish the story? And then, one answer to this, yeah.
I mean, would you say that about Shor's algorithm? Why would we expect quantum mechanics to help factoring?
Yeah, but Shor's algorithm, so here we're going from like P to NP complete. Shor's algorithm is already something with like intermediate complex. That's kind of a wild card, right?
Well, it could also be the case that the unique scheme conjecture is false. Right?
It could also be that, but then, my counterpoint to that would be I still expect that the answer is 0.878, but maybe you can't prove it using unique games, or maybe something else I'll say is that there are problems where, there's also an NP-hardness result here, but it's much worse than 0.878. So I think unique games might be more of a way of kind of addressing our inadequacy to prove lower bounds. But there are problems where we have tight kind of classical and we have tight approximation and lower bound results, and we don't need any conjectures. We just know that you're tied up to NP-hardness. So I'm happy to talk more, and this is maybe this is one of those things where it's going on camera, and then, like people will sort of replay it and shove it in my face, right? Like I don't know, right? But this is kind of my belief, and I might even contradict myself, like 15 minutes later if you let me get to that point in my talk. Okay, so so one answer to this is maybe let's not look at these classical problems. Let's look at quantum problems. So what I want to put out there is, can we come up with a picture like this for some local Hamiltonian problem, right? Like typically with local Hamiltonian problems, we don't think about worst case approximations. We think about like physically motivated scenarios like lattices and stuff like that, and we try to understand what's going on. But if we did think about worst case, could we come up with a picture like this for some model quantum QMA complete local Hamiltonian? So that's where quantum max cut comes in. Okay, so it's a special case. It's a two local Hamiltonian. In the poly basis, the term looks like this. And if you'd like, this is just a projector onto a singlet. So really all I'm doing is I give you some graph, and on each edge, I'm putting a singlet down. And I say two local here, but because we're a friendly audience here and we're in mixed company, there's really nothing kind of local about this in maybe a physical sense, right? These aren't like nearest neighbors, or they're not other kinds of geometric locality. All I'm saying is that each term has kind of two non-trivial polys in it. Right? So this is an arbitrary graph, and that's all I care about right now. So okay, so we look at this, and the goal is to output a maximum energy state, or if you want to make this formal, estimate the maximum eigenvalue up to inverse Pauli precision in the size of the interaction graph. And okay, so you could also output a state if you wanted. And then what I want to say is that this is actually, the way I've written it here, this is no different than the anti-ferromagnetic Heisenberg model. You want to find the ground state of this thing, well, all I've done is shifted the signs and added some identity. So why are we calling this quantum max cut? isn't that cheating? And you know, like, if people can write papers just by renaming stuff, then shouldn't we all be doing this, right? Like, yeah. So the answer is that if you just wanted to find the ground state, you know, the max energy state here, or the min energy state here, the identity doesn't matter. Physically, it's nothing. But if you care about approximations, identity matters a lot. So if you just wanted to approximate this, like, the best approximation you can get is within a log factor. But you know, when I add the identity here, I can get within a constant factor. And the identity kind of changes the hardness profile of the problem. It changes sort of, you know, where hardness will occur, what kind of techniques you can use, you know, how you can prove things. And so somehow putting the identity here is good for two reasons. One is that it turned this into projectors onto a singlet, which is kind of nice, you know, but of course it was already equivalent to that. But the second is it looks like quite like max cut. So if I get rid of the x's and y's here, I really just have, you know, the max cut Hamiltonian, but I've thrown in x's and y's. So yeah, I'm not cheating as much as you might think. So, okay. And then, okay, how does this work? What do we want to do? How do we make each term happy? So before, you know, we wanted to put different spins, classical spins, on neighboring vertices. And the identity term does nothing. And what makes this term happy on neighboring vertices? Well, when you measure in the x basis, you want to end up, you know, you earn a -1 on this term. I'm negating here, so I mean on the whole term, if you get the same measurement in the x basis, and then I get a +1 if you get different measurements. So, you know, you want both of them to be different. And then you want the same thing in the y basis and the same thing in the z basis. So one way of thinking about this is I took a classical problem and I've just kind of symmetrized it. So I want the same behavior in every basis because, you know, this is, this now becomes sort of SU2 symmetric, invariant, right? So I could say this about any kind of single qubit basis. And so I really want, it's like I have classical max cut simultaneously in every basis. That's kind of the idea. And the way you make this term happy is you put a singlet on an edge. So we know quantumly what the solution looks like, at least for a single edge. And then, you know, we're going to get entanglement problems if we go to a full graph. So does that sound okay? Any questions or okay? All right. So it's like math. Yeah, okay. So John Wright's slides are kind of, I'm not in sync with his slides, but thanks for letting me steal them from you, John. So we're going to, you know, let's skip over all this stuff. Okay. So now, let's get back to this idea of can we come up with a picture like this for some canonical, you know, local Hamiltonian problem? And so I'm not claiming quantum max cut is a canonical local Hamiltonian problem, at least not just yet, but let's see if we can do this for quantum max cut. So the first result was, you know, also in the paper where we introduced it with Sev Garibian, we used a technique very similar to the max cut technique, which is you come up with a semi-definite relaxation, but here you're using non-commutative semi-definite programs. You're using a non-commutative hierarchy. You know, this is like the NPA hierarchy or you know, quantum Lasserre. There are lots of names for it. So you use this to get a relaxation, and then you do some kind of rounding to get a solution. And you know, we got 0.498. And so for a while, we were like, okay, is 0.498 like the new 0.878? You know, is this like the quantum version of 0.878, right? And so if it is, great, you know, we're done with the story. And actually, it turns out it's not. So it turns out that, you know, what ends up happening is that 0.498 is kind of optimal if you're just using the most basic SDP you can, which ends up giving you the complete story for max cut. For max cut, use that basic SDP. It tells you everything you want to know. For quantum max cut, you kind of have to go to the second level. You know, you have to go to the next level up to start seeing some improvements. You can. Classically, we feel like that's not going to happen. And one thing that happens qualitatively is that you start getting monogamy of entanglement, you know, inequalities that fall out of this SDP. So, you know, for those who might be familiar with what's going on here, when you solve these SDPs, you get something that you could call a pseudo-density matrix. So it's not quite a positive operator. It doesn't behave like a true state, but it sort of approximates a true state. And the nice thing is that it has lots of properties of true states. Like, you know, you can prove that in the second level, you actually get a Lieb-Mathis type monogamy of entanglement constraints, even for the pseudo-density. And so that's what enables some of these approximations. So just using product states, it turns out that you can get a half approximation, and that's kind of the best you can do using product states, because even on a single edge, a product state can't earn you more than a half. So we kind of understand quantum max cut, very precisely with respect to product states, but Anshu, Gossett, and Morenz moved beyond product states and showed, you could get better than a half, and then we showed you could kind of do the same thing using this SDP picture, and then there's not much progress beyond that. So some results from last year, these came out at the same time. Yunyu Li's result, these are very nice in that they used SDP, but they used the output of the SDP as kind of parameters for a variational circuit. So, what's nice is when you do that, now you can start proving things about the performance of that circuit. So I feel like these kinds of techniques might also be important or useful, for other kinds of variational algorithms work, where when you combine it with like something where you're getting a bound, then you can actually maybe prove things. So the best known result is 0.562 for the general problem. You can get 0.582. Robbie King had this result, but it's only for triangle-free graphs. And then, there is a hardness result, and it's horrible. It's not the right answer, I can tell you that. But, we know that it's NP-hard to approximate this problem beyond 0.956. So we had a barrier between product states and general states, and then, we kind of have this barrier here, but there's this huge gap. And we don't really know how to fill it. We don't even know what kind of ansatz to use. So this ends up being a major problem. But I encourage people to, I think people with more physical insight, people with ideas. I mean, I think, I really think we're missing some of the major ideas here, and it'd be great, and I feel like maybe understanding them could have impact elsewhere. So this is our current version of, this kind of picture for quantum max cut. Okay, so more generally for quantum approximation algorithms, there's only been a handful of work. Again, this is the body of work where you're trying to prove rigorous bounds on worst cases. There's been some kind of a sparse selection of work up until recently, and these were all, just producing product states as output. And then in the last few years, we've been trying to take classical problems, and again, the same thing, trying to come up with quantum versions of them, and using the classical techniques to kind of come up with quantum algorithms for the quantum problem. And this is something you can do. This works. It becomes kind of boring after a while. Again, because we always run into the same problem. But the thing I want to say is that actually quantum max cut, we conjecture is kind of the hardest to approximate among all two local Hamiltonians where each term is positive. So in that sense, we think quantum max cut is a nice test bed. If you're trying to come up with new techniques for approximating quantum local Hamiltonians, quantum max cut is kind of simple to state, and we suspect it's as hard as anything else. And what's also nice is that classically there's a lot of inspiration in trying to come up with ideas, but of course you also need new quantum ideas. So if you want to work on this, and I already mentioned what's going on here. The slides will be available if you want to look at them. But if you're interested, I've highlighted 2 places where you could start, and I think they're reasonable introductions. Okay, so that's all I want to say about quantum max cut, unless we have time at the end to fill. Any questions or comments or? All right. More stuff to skip. This I might come back to later. So this is actually talking about where these relaxations come from. Yeah, let's leave it for now. Okay. So,
do you want to say anything why these approximate positive thingies help, or is that somehow?
Yeah. Okay. So you kind of twisted my arm. All right, so I'll tell you something. Okay. Great. So what I will tell you, I won't get into the details of, I'll skip this slide, but I can tell you what these pseudo-densities are. So what they are, if we wanted to write down an optimization problem, another way of writing down the maximum energy of H is, you have some operator, you want the trace to be 1, and then rho, the trace of rho times S dagger S has to be non-negative for all operators S. So this is just another way of saying that rho is PSD. So if we could put in a constraint like this for every S, then we will get a positive operator. So
in our terminology, these are states for operator systems. So there is, a theory which captures this. I mean, states for operator systems.
yeah. So where is this relaxation? Where's the pseudo part coming from, right? So the pseudo part is coming from the fact that what I could do is I could pick a parameter k, and I can say that I'm only going to insist that this condition holds for polynomials of degree at most k. So what I mean by that is, take this operator S, write it in the poly basis, and then only insist that when you write it in the poly basis, all poly terms are of weight at most k. So it only acts. Another way of saying it is it only each term only acts on at most k qubits. So if I insist that you're positive for terms of degree at most k, then it turns out there's a beautiful way of finding the best such rho tilde, and you could do it using a semi-definite program, and the semi-definite program grows as order n to the k. So if k is constant, you can actually find sort of the best answer to this optimization problem. So that's what's going on here. These are the relaxations. Okay, so now I want to tell you about quantum streaming advantages. So if we want to talk about streaming algorithms, some of you may have heard of classical streaming algorithms, but let's talk about space. Everybody talks about time. Everybody wants things faster, but actually, we really, if you're talking about near term, it's not just stuff that's faster. You actually want algorithms that use very few qubits. You kind of want space-efficient algorithms too. And so a streaming algorithm kind of fits nicely into the story where you have an algorithm, it could be this quantum algorithm, where you get to see your input go by, but you never get to store the whole input. I only get to see one piece at a time, and I only get space that's logarithmic in the size of the input. So, you could look at any measure of space where you're just sublinear in the size of the input. So I'm using less space than I actually have in my input. But the most interesting kind of cases are when you're extremely space limited. I only get logarithmic input. I can't, what could you possibly do if all I get to save is a logarithmic input, as I'm seeing all this data fly by? And so that's where this comes from. And it's actually kind of well motivated. You could, I'll give you some applications in a sec. But why do we care? Well, like I said, qubits are expensive, so we should also care about space-efficient algorithms. And we can also have these hybrid algorithms that use very, very few qubits, but we could use lots of classical bits if you wanted. And the idea here is when you're talking about models of computing like streaming algorithms, you do get that qubits are exponentially more powerful than classical bits. Like you can prove this. This isn't a Holevo kind of thing. You're not just storing data, but the way you're storing data coupled with the algorithm model, you actually get exponential advantages. So it's nice, right? It's nice to know that you can possibly get an exponential advantage. So, and like I said, this is actually provable. It's not like Shor's algorithm where someone can overnight come up with a better classical factoring algorithm and you're like, oh man, what do I do with all these quantum computers that I built, right? Like, okay, so what we want is we want algorithms that use very little space. And we're going to say we want algorithms that use not only few qubits, but also few bits. And so streaming, you could just think about space-efficient algorithms, and then you could say, okay, I could come up with some model, like what it means to be space-efficient. Our succinct input model was an example of this. But streaming is particularly when I kind of get input that comes in, and I'm not allowed to rewind. So I get an edge, I get another edge, I get another edge, and I have to act each time I see one of these edges. And then, together they represent some graph, but I'll never see all of it at one time. And this is useful, like on the internet, you have all this data flying by on any kind of big network, but your router has such limited space. And so if you want to compute statistics, or like, Alice is friends with Bob, Bob hates Charlie, et cetera, at the end of the day, who's still friends? If you want to compute these kinds of things, this kind of model is useful.
Sorry, can I?
Yeah.
Maybe I don't understand the stream like the thing on the left.
Yeah.
Has 3 edges in the thing?
Yeah, they're entirely, yes. So there's a mistake here. So yeah, I guess the point here is that, yeah, there's no point here. There's just a mistake. So, yeah. Okay. All right, so we'll move on. And so, you know, what can we say? So actually, like I said, we've known for quite a while that you can get an exponential advantage in this kind of model. So this was, there was the pioneering work, you know, that introduced the Boolean hidden matching problem actually gives a lot of provable classical quantum separation. So it gave a separation for streaming algorithms. So for this problem called Boolean hidden matching, I won't tell you what it is. It's not at all useful. No one had studied it before. You know, it solely exists to prove the separation between classical and quantum, you know, kinds of things, right? So this was great. It was amazing work. But the immediate question afterwards, very much like we're seeing today, is how to make it useful. You know, can you come up with these kinds of advantages for useful problems, or at least a problem that someone had actually looked at classically? And so it took a while, but my colleague John Colliher recently came up with one for triangle counting in graph streams. So, you know, I have this graph streaming model, and my job is to compute the number of triangles or estimate the number of triangles. And this is a useful parameter for like analyzing social networks. So, so he had this algorithm, which was great, you know, and I think it was kind of surprising, but good to see that the community was really interested in this. So, for example, this was a short plenary at QIP 2022. And you know, but one downside of this is that it's only a polynomial advantage. So then, you know, can we actually get an exponential advantage for some natural streaming problem? And okay, we thought, what about max cut? You know, everybody loves max cut. Or what about quantum max cut? Maybe, like I was saying earlier, you need to look at quantum problems if you want quantum advantages. So if I want some quantum streaming advantage, maybe I can't get one for max cut, but I could get one for quantum max cut. Nope, no quantum advantage here. You know, we proved you can't get one. But kind of surprisingly, if you just look at classical directed max cut, so this is like max cut on directed graphs, instead of max cut, you can actually get an exponential streaming advantage. So this is something that, you know, like everyone says, it'll be on the archive soon, but you know, yeah, it actually works, and this is based on a lot of recent work on streaming algorithms for classical constraint satisfaction problems. So then, yeah, is someone going to call me? Yeah, go ahead.
What does the sort of input in the quantum case look like? Is this still just
yeah, very good question.
state input, or
yeah, so the input is the graph. So you get to see, like we had before, you know, at each time I see some edge, and then you know, I can't ever rewind. So I see one edge at a time, and then I get to maintain a state. So based on the edge I'm seeing, I can enact unitaries on some state that I'm maintaining, and then I'm allowed to do measurements, you know, along the process, and then I have to answer the question. And here the question, by the way, is you know, sort of just the value, because you don't even have enough space to like store a solution. So you're just outputting some number that's supposed to be a good approximation to like the max cut value, you know, very much like the local Hamiltonian problem. In fact, there are actually some very strong connections between this kind of thing and these succinct, you know, graph models. Okay, thank you. So,
Can you say, sorry?
Yeah.
If you have these things, how long are you supposed to run these things? Like forever?
Until the graph is finite sized, and so you know ahead of time how many edges you're going to see, and so you run it until the end of the stream, and then at the end of the stream you have to output your answer.
Okay, but you cannot ask for an edge. You're forgetting them.
You're
right?
forgetting. You only see it once. Use it or lose it, right? So so it maybe in the interest of time, I'll call myself on this, right? So I said earlier, like, why should we expect advantages? Like, why would we need a quantum story to, you know? So I haven't told you. I haven't really given you enough information here to call me on this, but actually what happens is that there's, you know, this is very much like the picture is there's some approximation you can get using classical logarithmic space, and then classically, you know, to go beyond that, you need kind of root n space, and then if you have linear space, you can solve the problem, but quantumly, in this, what would take classical root n space, you could do it in quantum log space. So what does this have to do with quantum at all? Why is quantum somehow helping you get an advantage here? And I think the hint here is that this is really some, because of the succinct model, I think this is some kind of quantum problem, potentially hiding in disguise, right? So there's these succinct models like take you to things that might be quantum. And so I think, when you look at these different models like streaming and stuff, maybe you're running into this kind of territory.
So in the last case, can I think of that as a Hamiltonian or?
No, you could just trivially think of it as a classical Hamiltonian if you wanted to. But you could ask this same question for Hamiltonians, like that's what we did with quantum max cut, where you see a term, instead of edges, you'll see like terms of the Hamiltonian go by, and then you want to estimate the energy. So you could also do that, for example.
What would the directed mean?
Directed means that like when I partition the vertices, I only get credit. So I'm calling one side the left side, or I guess the right side, and then this one's the left side, and I only get credit for edges that go left to right. So when I'm doing my count of how many edges cross, I don't get credit for edges that go in the wrong direction. So it's just, in a
Hamiltonian, I just have interaction terms. So what is that?
we could talk more about this later, but you can also think about Hamiltonians as being like directed if there's some asymmetry. Like I could have, like Zi, Zj, but I could only have Zi and not Zj as a one local term, and then you'd have some asymmetry. Okay. So I think, I think we need to scratch our heads and maybe look at different models and stuff for these kinds of advantages.
So if you're trying to get to something else, I can wait till afterward.
Okay, yeah. Let me just say, so the last thing I wanted to say was, like max cut, quantum max cut, all of these things, they're in some sense unconstrained problems. You just have an operator, you're trying to find the max or min eigenvalue, you have no other constraints. But classically, in fact, most discrete optimization and most interesting discrete optimization is constrained problems. And so there's this constrained problem called vertex cover, which is kind of a very nice, almost prototypical sort of set covering problem. And, this is a vertex cover. You don't know what it is, but take my word for it. And so this is an NP-hard problem. And in fact, it was one of Karp's original 21 NP-hard problems. And what's really nice about this is that there's several two approximations known. And this is kind of the best possible you can do under unique games. So, in some sense, this we also feel is a solved problem. But what's particularly interesting here is to get this right answer, you don't need to do anything fancy like solve a semi-definite program. There's just a very simple combinatorial linear time algorithm that gets you this answer. And then you're done. And so then this raises the question, can we get a story like this for a quantum problem? So, you could write this thing, you could just take this classical problem and you could write it, you could shoehorn it into a diagonal Hamiltonian. I won't go into details, but the constraints, it's a one local objective, and then you have basically constraints on each edge just telling you that, you want to be outside of some subspace. So it's a very simple kind of, one local objective, but what makes it interesting is that you have two local kind of projectors that you have to satisfy. This is a hard constraint. So you could write this in the Z basis, and then, you could say, okay, this is a classical problem, like how do I make it quantum? Well, you could take inspiration from Alice and Bob, and you could just put a transverse field on it, right? So, so now when you put a transverse field on it, this becomes sort of a quantum problem. You can think of it as, again, we want distribution over diverse vertex covers, and we have no clue what the PXP model was, but after we came up with this, we realized that this is actually equivalent to the PXP model that comes up in understanding Rydberg blockade interactions. And, so we show that both of these problems are actually stochastic MA complete. But I think what's more interesting is that, just like I said before, there's a way to get an approximation for this problem without solving any kind of optimization problem. It's just very simple. It's a combinatorial algorithm. And so, the question is that I wonder if we can do this for more Hamiltonians, right? Can we use these classical algorithms as inspiration for new kinds of quantum algorithms that still end up being pretty simple? And then the last thing I'll say is that, this PXP model is related to quantum scars. And I asked like 3 of my closest physicist friends what a quantum scar was over the last few months, and I got 3 different answers. And it took me a long time to really figure it out, but I think I finally nailed it, So if you want to help me understand quantum scars, I would be grateful. All right, and so I think I can end there.
The